Let's take a look at the substitution method for solving systems of linear equations. The problem with the system of equations that we've seen in the past, like 2x, 3y equals 4, 5x plus 6y equals 7, is we could take either one of these equations and solve for a single variable, but we'd still have the other letter in it. So our goal for any method that we use to solve a system of equations is try to get down to one equation with only one letter in it. See, if we were to somehow say take this second equation and make it so it only had x's in it, we would then be able to come up with an answer for x and then use that to help us find y. So our goal for whatever method we use is to try to get down to one equation with one variable in it. Well, to do this for the substitution method, here are our steps. Step one, we're going to take one equation and solve for one variable. Step two, plug this into the other equation. Now once we do that, we'll have an equation that only has one letter in it. All we're going to have to do is solve that. And step four, we're going to use something that says back substitute. All right, so let's take a system of equations. Let's say we had, all right, here we have a system of equations. So step one, if we're going to use the substitution method, is to take one equation and solve for one variable. Now there's no wrong choice here, but there's maybe a better choice. We have four different things we could do. We could take the first equation, solve for x, first equation, solve for y, second equation, solve for x, or second equation, solve for y. So you want to kind of look into the future here and see what happens. If we were to take the first equation, solve for x, eventually we'd have to divide everything in that equation by 2. Notice this 3 isn't divisible by 2, that means we'd end up with fractions. Y'all don't like fractions, so probably not a good choice. If we were to take the first equation and solve for y, we'd have to divide everything by 3, everything's not divisible by 3, fractions. Second equation, solving for x, we divide by 3, everything's not divisible by 3. But you notice if we take the second equation and solve for y, we would not end up with any fractions. So that's what I'm going to do. I'm going to take this equation, I'm going to bring it up here. We have 3x plus y is equal to 5. All right, I'm going to solve for y. So y is equal to negative 3x plus 5. Now we're going to take this value, now that we know what y equals, and we're going to plug that into the other equation. The other equation is 2x plus 3y is equal to 8. So if this is what y equals, I'm going to take all of this and I'm going to replace it for the y. Now anytime you're substituting something in, make sure that you're using parentheses. All right, so that's 2x plus 3 times negative 3x plus 5 is equal to 8. Now notice we got our goal here. We got one equation with only one letter in it. This is something we should be able to solve easily by now. We go through it kind of quick. Combining our like terms, plus 15 is equal to 8. Get all your x's on one side, get everything that doesn't have an x to the other side, and divide. Okay, so we have half of our answer. We have x is equal to 1. Now we need to find a y value. Anytime the directions say back substitute, you can always go back to either one of the original equations and plug the value in for y. You notice you have an equation that only has x's in it. One of the nice things about the substitution method, because we already took one equation and solved for a letter, you have an equation that tells you exactly what the other letter will equal. So we know y is equal to negative 3x plus 5, and we just figured out that x is equal to 1. So y is equal to negative 3 times 1 plus 5, negative 3 plus 5, or y is equal to 2. Now remember, the solution to a system of equations with two variables here is a point. So the answer to this is the point 1, 2. Now just for a little bit of vocabulary, we saw last time that if a system has a solution, then we say that this is a consistent system, or this system is consistent. All right, let's try another one. All right, how about all right, this one's yours. Hit pause, see if you can solve this using the substitution method. All right, if you're back, let's see how you did. First up, using substitution method says take one equation and solve for one variable. There's no wrong choice. Any choice that you make, you should be able to get the right answer, but you should be able to see that the easiest choice would be to take the second equation and solve for x. So again, I'm going to bring this up to the top here. So x plus 3y is equal to 7. Subtract, so we get x is equal to negative 3y plus 7. We need to plug this into the other equation. So that's our other equation, so we're going to replace x with all of that. So that goes in the place of the x. Make sure that you're using parentheses here. So we have 4 times negative 3y plus 7 minus 5y is equal to negative 6. So again, this is just a linear equation. Should be fairly easy for us to solve. Negative 6. It's negative 17y plus 28 is negative 6. So we get negative 17y is equal to negative 34. And solving. All right, so now we have a value for y. We get y is equal to 2. Now once you have one value, back substitute. Remember, you can go back to either one of the original equations. Doesn't matter what you do, which one you put it into. But for the substitution method, we do have an equation that tells us exactly what the other letter equals. So since y is equal to 2, x is equal to negative 3 times 2 plus 7. X is negative 6 plus 7, so x is equal to 1. Now remember, the solution is a point, so you need to write the answer as a point. Since this system had a solution, we would say that this is a consistent system, or the system is consistent. All right, let's take a look at one more. Let's see. Let's go with 4x minus 6y is equal to 8, and negative 2x plus 3y is equal to 7. All right, again, take a second and see if you can solve this system. All right, if you're back, let's see how you did. This one you should got a weird answer. So here we need to take one equation, solve for one variable. Not a great choice here for any of them. So I'm just going to do the second equation, solve for x, because I like halves is the easiest fraction to work with, I think. So let's see. If I take this equation, plus 3y is equal to 7, and I solve for x, I get negative 2x equals negative 3y plus 7. Divide everything by negative 2. So we get x is equal to 3 halves y minus 7 halves. All right, pretty ugly, but we need to plug that into the other equation. Equals 8. So again, all of this mess goes in the place of the x. So we have 4 times 3 halves y minus 7 halves minus 6y is equal to 8. So I'll write one more step. So it's 4 times 3 halves y, 4 times 7 halves minus 6y is equal to 8. So let's reduce. 2 goes into 4 twice. That gives me 6y minus 4, or 2 goes into 4 twice. That's 14 minus 6y is equal to 8. Now notice here, when we go to simplify this, all of our variables went away. Now, the good news here is this is the same thing when we were solving any type of equation in the past. If all the variables go away and this is a false statement, then our answer is no solution. We say that a system is inconsistent if it has no solutions. Now, if we had solved this and we got down to a true statement, who knows, something like if we would have got 8 equals 8, that means that they're the same line. It means that there's infinitely many solutions. So anytime all the variables go away, that's going to be one of your two special cases, either no solution or infinitely many solutions. So for our substitution method, take one equation, solve for one variable, plug that into the other equation, solve, and back substitute.